All right. So on Friday, I left you with this idea that if you have a charged particle moving in a magnetic field, it's going to go in a circular path. This is going in a spiral because there's some kind of motion going parallel. It's going to continue to move unaffected that way. But perpendicular to that, it's always experiencing a force. Okay. One application, we talked about this, right? Okay. Oh, yeah. Another application is the northern lights, aurora borealis. Have you ever, you all have seen the northern lights before? Okay. Real life. So I might have saw it here in Indiana one time. It was, I don't know, questionable. Yep. The only time that I've seen them legit was like North Dakota or Minnesota or something like that. Um, so here, this is a direct consequence of charged particles moving in a magnetic field. So here's where it comes from.
The electrically charged gas is called plasma. The plasma drags the magnetic field further outwards. The magnetic field stretches and twists like a rubber band. And then the rubber band breaks. Several billion tons of plasma is hurled out from the sun. This is called a solar storm.
Okay. So let's talk about this with that, what you're getting at here. So plasma is the fourth state of matter. Solid, liquid, gas, the ones you're probably familiar with. At every level, every different state, we're increasing the amount of energy that the particles have. Solid, not much energy. They're like just together. Put some more energy into it, heat it up. The molecules now have more energy. Heat it up more. Now they're able to jump out of the liquid into the gas phase. If you heat it up more, at some point, the electrons are not going to be able to be bound to the atom, the nucleus. And so this dissociation, the separation of electrons freed from the nucleus, that is known as plasma, the fourth state of matter. Okay, so you got a bunch of ions. You have a bunch of charged particles moving. What happens when charged particles are moving? Creates a magnetic field. Okay, and that's what those rubber bands were showing, were the magnetic field lines of this solar storm. You good with that?
An invisible shield, the Earth's magnetic field, deflects the storm. The magnetic field.
Okay. So, first off, it's a really good thing we have a magnetic field, because if we didn't, these solar winds would rip off our atmosphere. Okay. So, this shows magnetic field from the Earth going one way, and this has this magnetic field from the solar winds, solar storm going the other way. They're going in opposite directions. So when they talks about rubber bands coupling together or like breaking, what that means is the total or the net electric field, right, magnetic field, is equal to zero. That's all that was getting at.
couple together and create a funnel where the gas streams down on the daylight side of the pole. This is the daylight aurora. The magnetic fields stretch further back and couple together. The magnetic rubber band breaks, and gas from the solar storm streams along the magnetic lines towards the poles on the night side. This is the nighttime aurora.
Okay. Now, when those when all those charged particles are free to go, they're going through that magnetic field of the Earth, and they act like, you know, those funnels that you put like a quarter in, the big ones, and like goes around like, and like okay, that's what's happening to the charged particles when they get down to the poles, like going really fast, and then they collide. They collide into gas molecules in our atmosphere, and actually they don't do that. They cause electrons to jump up to a higher orbital state, and then when they fall back down, they emit photons or light, and that's what causes the northern lights. Cool with that? So here are some videos of such northern lights. Okay, the different colors come from different types of gas molecules in our atmosphere being excited. So nitrogen, oxygen. And this is cool. This is the coolest. Where did that go? No, there it is. I had no idea they like fluctuated like smoke. Go with that. So, all right. Ooh, buddy. See if we have batteries for this. All right, have a demonstration back here. Can I say here? Can I be able to see? All right. So here, what I have is a really strong horseshoe magnet. Okay, it's like strongest I've ever seen permanently, like a permanent one. I'm like trying to get this through this hard to. So anyway, um, sometimes you can get a paper clip to like orbit. I don't know, it's kind of fun. Okay, so sure. So what I'm going to do is, what would happen if I allowed current to pass through this wire, and we put this wire through this magnetic field. So this is the North Pole, this is the South Pole. Which way is the magnetic field lines going in this gap? North Pole, South Pole goes out of north into south outside the magnet. Okay, so they're going which way? This way. So what part of your hand corresponds with magnetic field? Fingers. So stick your fingers going that way. Okay, so what part of your hand do you think corresponds with the current? Thumb. So current goes out of positive into negative. So the current through this wire is going to go which way? It goes out of positive into negative through this part of the wire. Where's it going to go? This way. So stick your thumb towards me. So which way is this wire going to be forced? Up. Hang on to that thought. Everybody see that? Okay. Good with that? So your hand should look like this. Okay. Now, if that totally, like, if it makes sense, we're good with it, and there's nothing, there's no little mental splinter in your mind going, then good. I would consider you a Ben Franklin follower, a conventionalist. If there's a thought in your brain that's like, wait a minute, a lot of electrons are doing things, then I would say you're a realist. If you're not a realist, which is totally fine, you're a conventionalist, just go ahead and close your ears, ignore what I'm about to say. But if there was some kind of mental splinter in your mind going, I thought there were electrons flowing, then here's my explanation. Okay. Electrons go which way compared to the direction of current? In the opposite direction of current. So electrons would have been flowing this way, out of negative into positive. but electrons are charged what? Negative, so it's going to be forced which way? Back of the hand, up. It'll work out either way. Here's the warning. Pick one way or the other. You cannot do both. Okay? You fully commit one way or the other. Do not dabble in both of them. Does that make sense? Yeah, so you're a conventionalist and you believe Ben Franklin, or you're a realist and you're like, there are electrons flowing. One or the other. Okay? Conventionalist, physics was set up for you. Like we had the right hand rule going before electrons were known. Okay. Okay. Second thing I want to show you, like if you want to come up here and feel this, what it feels like, highly recommend it. Come on up, just grab the wire, feel it. Okay, give this one a shot. Try this question. Show your neighbor. Correct answer is fingers are going this way in the direction of the field. Current's going into the board. You're forced up. If you're a realist, electrons are going in the opposite direction of current, negatively charged up. Next question. Show your neighbor.
I think he's standing up on it as it goes up.
Okay. Correct answer is out of the board. F. Next question. A palm pushing towards you.
But how is it? Your palm is the
Is the force.
Yeah.
Yep.
So if your palm is this way, what way your palm is facing is
Correct.
what way it's going.
Mm-hmm.
So if it's like this, I don't know.
Left. Yep. What? X is away from you. You're looking at the feathers going away from you into the board.
And then the whole.
Yeah.
Yeah.
You're looking at arrowhead
Yeah.
coming
I was
out of the
here,
page
so.
towards you. Okay, correct answer is G. Going parallel to the magnetic field. Current's going parallel, no force. Okay. Biggest application of this idea is a motor, an electric motor. What is the difference between a motor and an engine? So an engine is gasoline powered, like it's something that burns fossil, it burns something. Motor is electric, whether that's operated off of batteries or plug something in. Anytime you have anything that's electrical that has something moving, it has a motor. And this is conceptually at the heart of how a motor works. Okay, so a motor has some kind of magnet that creates a magnetic field. Okay, so magnetic field is going down out of north into south, and then it takes a wire and it passes current through it with this battery. Okay, so there's current going through this wire loop. Which way is this part of the wire loop going to be forced? Where magnetic field is going down, the current's going this way. Which way is this wire going to be forced? Magnetic field is going down, current's going this way. Which way is this part of the wire going to be forced? Show me. Magnetic field's going down, fingers go down, thumb goes this way. Things going to be forced into the board. Okay? Which way is this part of the loop going to be forced? You got magnetic field going down, you got current going down. Which way is that going to be forced? No force. Why? Parallel. Okay? You got current going through this way, magnetic field still going down. Which way is this guy going to be forced? Field's going down, thumb's going to the left, going to be forced out. How is this thing going to move if the top part being forced into the page and the bottom force part's going to be forced out of the page? Yep. Going to spin a little something like this. Okay. Now, this is engineered in such a way, this is called the bushing. So the current on this top part is always going that way. And the current going in the bottom part is always going this way. Okay. Have you, on like battery powered tools, you might have heard like brushless motors. Like this is known as the brushes. These wear out after a while. And so they've engineered to make brushless, but just to try to make a connection with something you might have heard of. Okay. So back here yet again. All right. So if you have ever taken apart any type of toy, battery powered toy, or something electrical that has a moving part, you'll find a motor. Okay, they come in assorted shapes and sizes. Some bigger than each other, some are smaller. Okay, but they all have the same basic components. Okay, if you pull one of these apart, what you'll find is you got magnets on the casing, creating a magnetic field, and you've got loops of wire around a iron core. These fit in like this, and they end up spinning. So I'm gonna throw some at you. Let's see, where did that one go? Dissected. There it is. So bend coming at you. Pass that around. Here are some that are like you can like look in and see. Nora, ready? Nice catch, Joey. You can kind of look at that. So you could take ah, all right, no homework tonight. No homework. And those are simulating the brushes. Now, these are the brushes. I was substituting that. So those stick in like that. The brushes go in like that.